Hey everybody, this is Mr. Beckstrom, and today I was asked to look at a problem from section 3.5. This is number 13, and it's dealing with displacement and looking at the velocity and acceleration with trig functions. So let's take a look at this problem here. I already worked some of it out here, but I'm going to go ahead and clear this out so we can kind of start from the beginning. So the first thing it says is graph the position function. Well, let me actually start here. An object oscillates along a line and its displacement in centimeters is given by the function y of t is equal to 33 times the sine of t minus 1, where t is greater than or equal to 0 is measured in seconds and y is positive in the upward direction. All right, so let's first go ahead and graph the position function from 0 to 10. That's our t. In this case, t is our independent variable. We're going to go ahead and use x in our calculator. They're interchangeable. So let's go ahead and put this function in there. So we're going to put 33, open parentheses. And also make sure that you're in the radian whenever we graph trig functions. We always want to be in radian there. So once again, so 33, open parentheses. We're going to do sine. If it automatically opens up a parentheses like that, make sure after you put your variable in there, you close your parentheses because it's only the t in there. It's not a t minus 1 inside the actual angle there. It's just the angle, and then it's minus 1 like this. And the 33 is on the outside. So this is what it looks like. It'd be easy to kind of mess this up and put that minus 1 inside that angle, which we don't want to do. Now let's go ahead and fix our window here. So we want to go from 0 to 10. So make sure that your x-min and your x-max is from 0 to 10. And our y, it looks like we have an amplitude here of 33. So without really knowing how high or how low this thing could go, it could shift up as high as 66 and it could go as low as negative 66. So let's go ahead and just to give it some space, I'm going to go from negative 75 all the way to positive 75. Just to make sure I can see this entire thing here. All right, and go ahead and graph this. And so this thing is completely below the x-axis. And all right, so this is what it looks like. So if we were asked this question, we should be able to match this up with whatever one of the multiple choice graphs that it gives us. All right, second part, it says find the velocity of the oscillator. So that is just the derivative of our function. So the velocity is just the derivative. So hopefully we have seen what the derivatives of our trig functions are. So let's kind of work this out here. So the derivative of this, which is just equal to the velocity of that, is going to be equal to, well, let's go ahead and find the dy with respect to time of, and let's go ahead and distribute that 33 out here. So that's going to be 33 sine of t minus 33. Right, so this is just finding the derivative with respect to t. So this is just going to be the derivative of sine is just cosine. So our answer should end up just being 33 cosine of t, and minus 33 just falls off because it's a constant. So this here is our velocity. All right, not too hard. And then it says graph the velocity function. All right, so let's go ahead and graph it. We'll leave it right up with this one. So go back to y equals, put it down here. So this is 33 cosine of x. Go like that. Go back to graph. And so this is the graph of the derivative or the velocity function there. So we should be able to go ahead and match that up. That looks like a pretty standard cosine function, just the amplitude is much larger than a normal cosine function there. 33 times larger, as a matter of fact. All right, and then we go to C here. It says, oh, we've already graphed it there. And D, it says, at what times and positions is the velocity equal to 0? Well, let's go back over here. And this being kind of a normal velocity function, or normal cosine function, just with a higher amplitude, it's just going to be wherever the cosine is equal to 0. So where's the cosine equal to 0? Well, thinking back to our unit circle, where are my x values equal to 0 on the unit circle? So that would be pointed straight up and straight down. So that's pi over 2 and 3 pi over 2. So that would give me a couple of those, right? So pi over 2 and 3 pi over 2. And then they also want positions, right, of where that is. So we'd go back to our position function and just put those values in there. So where at pi over 2, looks like I'm right here at 0 there. So pi over 2, 0. So pi over 2, 0. And we have another one here at 3 pi over 2. And let's see where 3 pi over 2 is. 3 pi over 2 is right here. And what is this value? Well, if I just go right back out here and I go to vars, go to y variables, pull up my y1, and I'm going to say evaluate my y1 at 3 pi divided by 2. Should give me what that position is, which is negative 66. So this one is negative 66. And I can keep doing that for a couple of more if I'd like. So you can do what, 5 pi over 2, 5 pi over 2. And if you put that into your calculator, you should get 0. And you can just keep on as far as you want to. All right. Each time you add pi, or excuse me, pi. So it goes from pi over 2 to 3 pi over 2 to 5 pi over 2. So yeah, each time you add another 2 pi over 2 or pi, you'll get another answer there. At what times and positions is the velocity a maximum? All right, well, let's take a look at our graph here. So at what times and positions is our velocity a maximum? So if I go look at my graph here, now this is my my velocity is the red graph here. So it looks like it's at 0, right? It's at a maximum right here. It looks like it's again at 2 pi, and it's going to be again at 4 pi. There's other ways to figure that out as well, but you know, visually it's going to be maximums there at those points there. So 0, 2 pi, 4 pi, dot, 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 dot. And once again, if we wanted to find those positions, we would just put each one of these into our position function. So I could go out of here again. So at 0, you go to vars, y variables, and evaluate this at 0. So at 0, we'd have negative 33. And this is going to make sense because if I go back to my graph, if you look at the blue graph, at 0, look how steep that that tangent line is right there. That's so that's going to be a pretty extreme velocity right there, right? And then we kind of slow down, slow down, slow down, and then we're kind of going down here. And then as we're coming back up here, right about here, we have another steep velocity line, right? Or excuse me, another steep tangent line here, right about where the velocity graph maxes out again. So that's how we can kind of visually see this on our two graphs. All right, so you can find all of those points just by putting those x values back into our position function. And then finally it says the acceleration of the oscillator is a of t, which is the derivative of v of t. So if we just take the derivative of, what is that, with respect to t of our cosine one, right? So that's 33 cosine of t there. That will give us our a of t, which is equal to, and the derivative of cosine is negative sine. So it just changes that to a negative, and that'll give us negative 33 sine of t. And that is our acceleration. So let's go ahead and graph that, and then I think we're done. So graph, yep, y equals, go down here to negative 33 sine x do, and graph. And this is our acceleration function, which is kind of the same thing to our velocity function as our velocity function is to our position function. All right, I hope some of this made sense to you. I know this kind of looks just like a big mess, but if you break it down, it's all math. If you have any questions, let me know, and I hope you have a great weekend. Thanks.